So the OH bonding to the right one, or it could be the OH bonding to the left one and the H bonding to the right one. In both cases, you're going to get different molecules. The rule stated that the H atom likes to bond with the carbon that's bonded to more H atoms already. I mean, that was the rule. That if you look at a molecule, then the H prefers to bond with the carbon atom that's already bonded to more H atoms. I can do another example, and that example is let's think of this molecule. You have CH3, C, and there's a double bond, and C, and there's H, another. So here's your molecule, and you're reacting it with HBr. So the question is, where would the H and where would the Br get bonded to? I mean, there's going to be a major product and there's going to be a minor product. So you're going to get two different types of products. So it's either going to be that if I pick the molecule and focus on these two carbon atoms over here, so there's this carbon atom and this carbon atom. Uh, which one would the H get bonded to? Mohammed, any idea?
It's the first one on the left side because it's a six hydrogen bonded to it.
No, it's not. I mean, this one has zero
Wait,
hydrogens.
oh, it could be zero. Yeah, never mind.
Okay, because you have to focus on that carbon atom. How many H atoms is this carbon atom bonded to? So this one is bonded to zero hydrogens, and this one is bonded to exactly one hydrogen, right? So so the H atom would prefer this carbon atom. It's going to prefer this carbon atom and the molecule that would be formed. Isa, is this clear?
Yes, sir.
Acha, so you would have double bond and you would have CH3 and H. So this H would prefer to bond with this carbon atom. And the Br would then by default bond with the other one. And that's going to be called your major product. That's your major. So that's your major product. The other way around is also possible, but that would be called your minor product. Now the reason for this, why is this happening? Why do you have uh, but why is this rule there? Why does H like to bond with the carbon atom that's already bonded to more H atoms? So we're going to talk about the explanation now. And remember, you can be asked about the explanation in the past paper questions. What's the reason for this? And the reason is that if I have an unsymmetric molecule, and let's say I'm going to draw two versions of this. So let's say this is version number one, and the same molecule. Now I'm trying to draw the mechanism now. So how would the mechanism look like? Okay, so let's focus on the mechanism. An HBr molecule comes in. The H is positive, and the Br is partial negative, and the electrons in the bond over here. The positive H would attract the electrons from the double bond, and the Br is going to get repelled because the H would get attracted to the double bond, and the Br is negative. It's going to get repelled. So, so that's the first step. That would happen to the other one as well. So the Br breaks off. Okay, so let's not talk about Br. Let's think of this H. It's the H atom that's actually attacking it, right? The H is now fully positive because the Br took its electrons. Mohammed, is this clear so far? Isaac, clear?
Yes.
Yes.
Okay, so there's another H plus one over here that's attacking it, right? Now, in all these reactions, it's always usually the H that initiates the reaction. The H is the partial positive part of the molecule. Like in water, it is, in HCl, it is. And it is the one, it is the trigger. It's the one that goes and starts to pull the pi electron cloud in that alkene, in that double bond. Now, two things would happen, that either the H goes and bonds with the carbon on the right. I mean, it's going to pull the electrons in the double bond, okay, pull those electrons towards itself, and it would bond with that particular carbon atom, and the positive charge would now be with this carbon atom, this other one, because the H pulled its electrons in the pi electron cloud and kept them towards itself. Okay, Ethan, is this clear?
Yep.
Or the other thing would happen, that the H plus one goes and bonds with the carbon on the left. So it pulls the electron in the double bond, pulls them towards itself, and bonds with that particular carbon atom, and the positive charge shifts and goes to this carbon atom, right? So two things are happening, two totally different scenarios. Either the H bonds with the carbon on the right, or it bonds to the carbon on the left. Now, so two carbocations are formed, two completely different carbocations are formed. Now, according to Markovnikov's rule, this is what's more likely to happen. This is your major product. Why? Because the H likes to bond with the carbon that's already bonded to more H atoms, two of them, whereas this one is bonded to just one of them. Okay, this is not going to happen. The H doesn't like to bond with the carbon that's bonded to lesser H atoms. Okay, Mohammed, is this clear? Is this clear? Ethan, is this clear?
Yes.
Yep.
Acha,
Yes.
so what's so special about the left one, and what's so special about the right one? Now, the whole thing boils down to the positive charge on this carbocation. Uh, Focus on the positive charge on this carbocation. Okay, this carbocation is positively charged, so I'm just going to put that positive charge on that carbon. This carbon atom is also positively charged. And I'm going to circle them as well. So positive carbon atom, this one is also positive. So you can see in both cases, there's this carbon atom which is positively charged in both cases. Uh, but one of the positive charge is bigger than the other one. So why is that bigger? Reason is, let's focus on this carbon atom first. It has a carbon atom over here on the left side, so that's 6 electrons over here. Carbon has 6 electrons. There's a carbon atom to the right, so there are 6 electrons on the right side, and there's a hydrogen atom on the top, so that's 1 electron on the top, right? But let's so that's 1 electron on the top. So how many electrons are surrounding? Well, how many electrons are surrounding this carbocation? There are a total of 13 electrons. So this positive charge in the middle of the molecule is going to start pulling, or slightly pulling, the electrons towards itself, right? Because it's surrounded by electrons. And that would decrease the positive charge. So the positive charge would be smaller. I mean, the positive charge would lose its strength. It's not going to be a very large positive charge. It's going to be a relatively small positive charge. Not all plus one charges are exactly the same. So because the positive charge is present in the middle of the molecule, and there are carbon chains on both sides, carbons have lots of electrons. So it's surrounded by electrons. So the electrons are going to get pulled towards this positive carbocation, and the positive charge would kind of get neutralized. It's going to be smaller, relatively smaller. Is this clear, Ethan? Is this clear, Mohammed? Aiza, clear? है?
Yep.
Yes.
Achha, so
Yes.
what about this? What about this other one? Let's focus on this other one. Uh, how many electrons is this surrounded by? There are six electrons over here, and there's one electron over here, and there's one electron over here. Now, by looking at it, its neighborhood is kind of, it doesn't have a lot of electrons because it has more hydrogen atoms. Hydrogens don't have electrons. So the same thing would happen over here as well. It's going to try and pull the electrons and try to neutralize itself. But there are not a lot of electrons around. So in a relative sense, this is going to be relatively larger. ठीक है ये भी is this clear Ethan, is this clear, Mohammed?
Yeah.
Yes, it's clear.
Okay, so this one is going to be relatively larger. The next part is this larger carbocation is the reason why it's going to be unstable. What does that mean? That means, now focus on this one, that we've already discussed that the positive charge is large. Why did it get the positive charge in the first place? Because there was an H plus one that came along, right? I mean, there was an H plus one that was roaming around, and that H plus one pulled its electrons from the double bond. I mean, previously it didn't have a positive charge, right? So, one second. So, previously, this carbon over here did not have a positive charge. Why did it get a positive charge? Because there was an H plus one coming around, and it pulled the electrons, right, from that carbon, and the carbon got a very large positive charge. So if it's getting a large positive charge, the H plus one would not be able to actually pull electrons away from it. It's going to attract the electrons back again. And the H plus one would fail to actually pull those electrons because the carbon gets a very large positive charge and it would pull those electrons back. It's going to have a very strong attraction for those electrons. So it's not going to let go of those electrons in the first place. Is this point clear? Aiza समझ आई बात? Mohammed, is this clear? Ethan?
Yes.
Yes.
ठीक है अच्छा why does this happen over here on the other side? Okay, the positive charge is smaller. So if the H plus one comes along and well, that was the reason why it was getting a positive charge. So if the H plus one comes along and pulls electrons, well, these electrons belong to this carbon atom. So if it pulls those electrons away from it and tries to bond with it would allow the electrons to go away. Because the positive charge is smaller, it can get electrons from some other place. I mean, there's so many electrons around it that if the double bond electrons are getting pulled towards the H plus one, it doesn't mind because it can get electrons from some other place. So that's the main reason why this one is stable and more likely to form, and this one the reaction would not proceed through this path because this carbon atom would not allow the H plus one to take its electrons away. So is this clear? Ethan, Mohammed, everything, is this clear? Any questions about this?
So like the H plus and the carbocation with the larger plus charge gets repelled in a way.
The reaction would not be possible by that path. I mean, the first part was they're not going to get repelled. Because the carbon never had a positive charge, right? It only had a positive charge because so there is no repulsion. There is attraction. Initially, if the double bond is not broken, the carbon doesn't get a positive charge. Do you get my point?
Yes.
The only fact is that if the H plus one tries to pull the electrons away and tries to bond with them, uh, then its positive charge is gone. The carbon gets a large positive charge, and that large positive charge is going to immediately pull the electrons back. It won't allow the electrons to go towards the H plus one over here. Ethan, Mohammed, is this clear?
Um, can I just clarify when you
Yeah.
said the carbon, basically the carbon positive, it's smaller because it's pulling more electrons?
I mean, this one, right? This one over here.
Yeah.
It's positive because it's surrounded by a lot of electrons. So think of a positive charge that's surrounded by a lot of electrons. So it has a lot of electrons available. What does positive charge do? I mean, it pulls electrons, right? So because the neighborhood is surrounded, I mean, it's surrounded by large groups. There's a carbon atom over here, a carbon chain on this side. Uh, so it's going to pull the electrons, and the positive charge would become smaller or would kind of get neutralized. Is this clear?
Oh, the charge gets smaller.
Yeah, the charge gets smaller.
Okay. Yeah. Thank you.
I said, so what you're going to write is the explanation for this is, so it's going to be a two line explanation, which is you're going to write that carbocations with more carbon chains or alkyl chains are more stable as they have a lower charge density or smaller charge density. That's it. Okay, that's it. That the H likes to bond with the carbon that's already bonded to more H atoms, because that results in the formation of a carbocation, which has more alkyl chains and therefore is more stable. As they have smaller charge density, another thing that you can add is that the alkyl chains have an electron donating effect. Like if you have more alkyl chains, so those alkyl chains have electron donating effect. So you can add that as well. And that's pretty much it. So that's the explanation for Markovnikov's rule. Is this clear to
Yeah.
everyone? Okay.
Yes.
And so now moving to the next part. This was all about mechanisms. I think we did the last one as well. We talked about, yes, we talked about pretty much all the electrophilic addition mechanism. Now the other thing that we're going to do is we will be talking about oxidation of alkenes. So oxidation of alkenes. And what happens in oxidation of alkenes? Remember, this is something that you did not do in O levels. You did all the addition reactions, not the mechanisms, but you did the addition reactions. Oxidation, you never studied oxidation of alkenes. Now, remember, there are two types of oxidation of alkenes. Number one is you have mild oxidation. So you have mild oxidation, which is that you have cold dilute. So the conditions for mild oxidation, you need an oxidizing agent, which is cold dilute or alkaline KMnO4. Now, all three are mild conditions, are considered mild conditions. So cold, dilute, and alkaline KMnO4. Remember, KMnO4 is that purple colored substance. It's purple in color, and it gets reduced to brown and then colorless. Now, this brown thing is usually MnO2, and colorless thing is Mn2 plus. So that's usually the reaction sequence. The KMnO4 getting reduced. What happens in mild oxidation? Mild oxidation, you have an alkene. Let's say you have CH3 and you have C double bond C and there is H and you have this is your oxidizing agent, cold dilute KMnO4. What would happen is that the double bond, it's going to be like an addition reaction that the double bond is going to break. So the double bond would break and a diol would be formed. Both carbon atoms, OH groups would get added to it and diols are going to be formed. Is that clear? I mean, that's a simple reaction.
Yeah.
Yes.
Okay, diols are produced. So this is mild oxidation. What you simply need to do is, okay, whenever you see a double bond, just make it, just add OH groups to it. Like if I have a molecule, let me draw a molecule. So if I have this molecule of there's a double bond here and there's a double bond here. Let's say this is the molecule and I want to do mild oxidation for this molecule. What's going to happen is the product of this reaction would be that, so the product would be that all the double bonds would be gone and you're going to have OH groups attached. There's going to be an OH group attached over here and an OH group attached over here. That's the first thing. The double bond, the carbons that were making the double bond would vanish. And over here as well, you would have OH groups attached and you would have OH groups attached to it as well. ठीक है? Is this clear?
Yes.
So the next part is the tricky part, which is which is strong oxidation. So the second part is strong oxidation. Now, strong oxidation is that the conditions are going to be you're going to be using the same oxidizing agent, and in strong oxidation, the conditions would be strong. You will be having hot, concentrated, and acidified KMnO4. So you're going to be having hot, concentrated, acidified KMnO4. The conditions are strong, and they would be the rest of the steps are slightly more complicated. The first thing is that whenever you see a double bond in a molecule, unlike the previous case, what would happen is all double bonds look like this. So what would actually happen is that the double bond would break completely. Uh, Complete breakage. It won't turn into a single bond. It's going to completely break, and the molecule would split into two parts. And there would be different scenarios. Number one, that if the double bond carbon was bonded to two hydrogens, that's scenario number one. Okay, that's the first scenario. Then this type of structure would get converted into carbon dioxide and a water molecule. Then you have scenario number two, which is that the double bonded carbon is on one side bonded to a carbon chain, and on the other side it's bonded to an H. Now, what would happen is, in this case, what would happen is that it would first change into an aldehyde, So it would be serial bond O and H, and then it would further get oxidized to a carboxylic acid. So it would change into, the C would change into RC double bond O and OH. Because that's scenario number two. And let me write, it's going to form aldehyde. And eventually it would form a carboxylic. Eventually it would form a carboxylic acid. And then you have scenario number three, which is that in scenario number three, one second. So in scenario number three, you will have that once the carbon breaks off from the double bond, if it's bonded on both sides by R groups, then that thing would change into a ketone. So it would be double bond O, and this side would be R, and that would be a ketone. So ketone would be formed. So there are three completely separate scenarios. Okay, that's one. So the double bond, remember the double bond is going to completely break. And then you would have to decide what's going to happen to this carbon atom. And remember, it's any change that would happen to the carbon that was bonded to the or was making the double bond, not to any other part of the molecule. The rest of the molecule remain exactly the same. It's only this carbon that would change. So if it's bonded to two hydrogens, then it would change into carbon dioxide and H2O. If it's bonded to a carbon chain on one side, the carbon chain would remain pretty much exactly the same. It's the change would happen to this carbon atom that was previously making the double bond. It would change into an aldehyde, then change into a carboxylic acid. And you're going to change it into a carboxylic acid. The reaction doesn't really stop over here. It goes all the way to completion to a carboxylic acid. And the same is that if it's bonded on both sides by a carbon chain, the carbon chains should not change. They should be exactly the same. This carbon would change. It would change into a ketone. So is this clear? We'll understand this better if we do an example. So let's try and do an example of the same molecule. Let me draw a different molecule now. So I have a molecule which is, so there's so this molecule. Let's try and oxidize this molecule. Now, one thing that should be done is, first thing, I'm going to start the working on this molecule because the skeletal formula doesn't show hydrogen atoms. So I'm going to or draw the hydrogen atoms, add the hydrogen atoms. So this one will have, but let's do the working on a separate molecule that is getting oxidized. So I'm going to do all the working on this. Okay, so it's this molecule. There's a double bond here and a double bond over here, and there's this bond. I say, anyways, let's start doing the working on this. This carbon atom. Remember, focus on the carbon atoms that are part of the double bond. Now, this one is bonded to two hydrogens. How did I figure out that it's going to be bonded to two hydrogens? Because why? Because it's making two bonds, so there would be two hydrogens. So anyone, Mohammed, Ethan, Aiza, which scenario is this one? Like the double bond would break completely. So what would this carbon atom get converted into?
Carbon dioxide and water.
Okay, because it's C with two H's, right? So that's option number one. That if the carbon that was making the double bond is bonded to two hydrogens, so it would change into carbon dioxide and water. So let's break it off. So I'm going to get rid of this. This is gone. It has changed into carbon dioxide and water. What about this other one that's left on the other side of the double bond? Which scenario is this one? One, two, three. Which one? Mohammed, any idea? Aiza, any idea? Like the carbon on the other side of
Is it three? Number three.
Okay, because there's a carbon chain on this side and there's a carbon chain on this side as well. So this is number three. That if the double bond, the carbon that was making double bonds was bonded to two carbon chains, then it would change into a ketone. So all the change would happen to this carbon atom. It would change into a ketone. You just have to add an oxygen to it. So that's it. Then this one, you're going to break this double bond. Uh, Not this one on the. Let's do the working on the molecule. So you're going to break this double bond, and once you've broken this double bond, what this carbon atom, what would it change into? Again, it's bonded to two carbon chains. I mean, I'm going to break the double bond. Take it. The double bond is going to be completely gone from here. The remnant of the double bond is there just to uh, clarify things. So this carbon atom over here is bonded to two carbon chains. So this would also change into a ketone, right?
Yes.
And what about this top one? The top one, it had one hydrogen as well. Like it
Is
was
it
making,
the second scenario?
it was making a double bond, carbon chain on one side, and there's a hydrogen atom on the other side. So it's the second scenario that if you have one hydrogen, then it would change into, eventually change into a carboxylic acid. So turn this particular carbon atom, so turn this particular carbon atom into a carboxylic acid. It would be double bond O and OH. So it would change into a carboxylic acid. So is this clear? This is going to be your product if you oxidize this. Is this clear, Mohammed? Ethan?
Yes.
Yeah.
Yes, it's clear.
Okay, then try and do this question, TK, right now. So you have this molecule, and there's a double bond over here and over here. Tell me what the product of strong oxidation. Remember, I'm talking about strong oxidation. That's number one. Question number two is so question number two is you have this molecule and there's a double bond here and a double bond here and this thing. So tell me the products of the strong oxidation of both of these molecules. And send me the answers. What would happen is in this one, what would happen is let's just keep this. These are the two carbon atoms, right?
Yeah.
So the double bond is going to completely break, gone in the middle. What would this change into? This was scenario number two, right? It was going to form a carboxylic acid.
I see.
And this one over here is also scenario number 2. It would form a
Carboxylic acid.
carboxylic acid. This one over here, this carbon atom, both sides has a carbon chain, so it's a ketone. This one also, both sides ketone. So the double bond is going to completely break in the middle. This would change into a ketone, and this one would also change into a.
Oh,
So you're basically, getting the same molecule. I mean, both of them are exactly the same. I mean, you're getting two different molecules. It's splitting up, but it's forming the same molecule, right?
yeah.
So let's practice more of them in the next class then.
All right. Okay.
Okay then.
Thank you.
Yes. Okay. Thank you.
Okay, bye.
Bye.